Hi, everyone. So thank you for joining. Today, I want to talk about work that we've done setting up a data collection and monitoring solution for researchers and scientists that run Pegasus workflows. This talk can be useful to you if you're looking to better your data collection and workflow monitoring capabilities. So whether you're a single user or a research group. For most of this talk, I'll be going over the data collection pipeline that we've put together and how you can get started using it for your own work. But before I do that, I want to go over some background information as to how this all came about. So the Laser Interferometer Gravitational Wave Observatory, or LIGO, it's a gravitational wave research facility that is operated by Caltech and MIT. And some of the research that they conduct is using a software package called PyCBC. So their analysis pipelines are organized as Pegasus workflows. And these pipelines are then executed on distributed resources such as Open Science Grid and Exceed. So this image on the right here is from one of their cool discoveries where they detected gravitational waves from the collision of two black holes. So the science here is pretty serious stuff. And so their work requires some very complex workflows. So what do these workflows look like? So on the right, you can get a sense of what the topology of these workflows look like. An advanced PyCBC workflow contains 60,000 compute tasks, uses 5,000 input files totaling 10 gigabytes, and produces 60,000 output files totaling 60 gigabytes. So after the workflows are complete, then PostRun Analysis are done, and then plots like these are generated. So these plots are distributions of various PyCBC specific metrics. So the point I want to get across here is that there are some challenges that come with executing workflows of this size. So for example, how do you go about successfully debugging such a complex workflow without spending too much time? Or what if you want to monitor and analyze multiple workflow runs that are submitted by various users and submitted from different submit machines as well? So to address these challenges, we've done some work that was recently funded by the NSF. So Dibbs, Domain-Aware Management of Heterogeneous Workflows, Active Data Management for Gravitational-Wave Science, is a collaboration between Syracuse University, LIGO, Caltech, and us here at USC ISI. So Dibbs here stands for Data Infrastructure Building Blocks, which is kind of what this talk is going to be about. So this work is all about empowering LIGO researchers in their study of gravitational waves. And to do so, we set out to develop new data management techniques in Pegasus. We wanted to improve data access for LIGO researchers, enhance workflow monitoring capabilities, and then also to enable analysis to be done across multiple PyCBC workflows. So now as a result of this work, we've developed Pegasus Extensions to capture runtime provenance metadata. That data is then inserted into a relational data store, and then also an Elasticsearch instance, which will be the focus of this talk. So also we've supplied monitoring solutions using Kibana, which is useful for data exploration, and also Grafana, which provides us with nice interactive dashboards. So now that brings us to the main part of the talk, which is the data collection pipeline that we've put together as a result of the Dibbs work. First, I'll be giving an overview of the pipeline itself. Then I'll briefly describe each component. And then finally, I'll show you how you can get started using this for your own work. So this is what the pipeline looks like from a bird's eye view. I'll be going over the flow of data from the point when it is created and then until it is inserted into the data store and then made visible to users. So say that you've submitted a workflow and then at some point a job completes or fails. In this case, we'll just say that it was successful. At that point, job information is sent to Pegasus Monitor D, which is running on your submit node. And you can see that with the red arrow right over here. And then Pegasus Monitor D sends that information over AMQP, which is the active message queuing protocol, to a RabbitMQ instance. The message goes through an exchange, and then at which point it is sent to a single queue to be consumed. Then Logstash is the next step. It consumes a message from the queue and then inserts the data into an Elasticsearch instance under an index that we've called Pegasus-composite event-star. An Elasticsearch in index is just a collection of documents that are related to each other. So the first way that you can access this data that was just inserted is to use Kibana, which is accessible for the browser. I'll be going over that in the coming slides. And then the second way that you can access this data is through a Grafana dashboard. So that pretty much covers the flow of data from start to finish. Now I'm going to go over each of the components individually so you can kind of get a better idea of what their role is in this. So starting with RabbitMQ, it's a lightweight message broker. And in our case, it provides several advantages. So the first being that it promotes decoupling between Pegasus Monitor D and the underlying data layer. So this means that you're able to swap out Elasticsearch for some other service, such as a NoSQL database, if you wanted to. Of course, we've set up this pipeline and the visualization tools to work with Elasticsearch, but you wouldn't have to worry about the transfers between Pegasus, Monitor D, and RabbitMQ. Also, you could augment the current setup by adding another queue and another data storage service. So let's say you wanted data to go into Elasticsearch, but also some other database, you could do that too. And then also RabbitMQ can be deployed in a distributed environment to meet any sort of high availability requirements that you might have. Although in our practice, we haven't had to do this, but the option is there for you. So the next part of the pipeline is Elasticsearch, Logstash, and Kibana services. This is also known as the ELK stack. It's all sort of run by the same company. So Elasticsearch, it's a distributed RESTful search and analytics engine. It's useful for log analytics, application performance monitoring, and any kind of collection of infrastructure related metrics. But essentially we use it as a document store. Now, in order to get data into Elasticsearch, we use Logstash, which is a server-side service that can consume data from some source, perform some filtering and transformations, and then insert it into the data store. So what's great is that Logstash works with a variety of input sources, and that includes RabbitMQ, HTTP, Amazon S3, or even TCP sockets. And then finally in this stack, we have Kibana, which is for data visualization and exploration, and it's accessible via your web browser. So this lets us poke around at the data in our Elasticsearch instance. And in practice, we found it very useful for just exploring our data, looking through the events for each job, and also for just debugging workflows. So I'm going to do a quick overview of what this looks like here. So let's see. I guess my link is not working. One second here. There we go. Okay, so this is the Kibana user interface. When I click on Discover, we have here data from all of the jobs that have occurred in the last 15 minutes. And so this is nice because you can go and set this range back to a day, a month, or a year. And then you can also filter for specific things. So for example, if we look at this item right here, this is from a job. This is a compute job that was run on this host name. And this is the DAX file that was used when the job was submitted. Also, You can see standard out and standard error is over here as well. So if you wanted to filter through those to look for certain information, so like here we have exit code, you could do that. And also you can have, you can filter by user. So if I wanted to look at all the jobs that this user submitted, I could click filter by value. And then now, all the data from that user gets pulled in the last 15 minutes. So, you know, it's very good for just kind of looking around at your data. Okay, so finally we have Grafana, and that allows us to create browser-based interactive dashboards. And Grafana is good because you can pull data from different types of data sources, including Elasticsearch, as we've done here. But you could also use you could pull data from MySQL if you want, or there's support for NoSQL databases. We really like the fact that Grafana enables us to share data with others without exposing the underlying data source. And in practice, we found that the dashboard that we've developed has been useful for several different ways. And that would be enabling researchers and system admins to get a holistic global overview of all of their PyCVC analysis workflows that are being run, but also to be able to monitor computational resource usage. And because the data comes in, and you can just refresh the dashboard, you can identify trends and errors as they occur. So that might be useful as well. And we can take a look at what this dashboard looks like. So just like in Kibana, you can set a range for which you want to pull data. In this case, for the purposes of this demo, I have it set to December. You can filter by Pegasus version, the host that the workflow was submitted from, and a specific user as well. So these 4 workflows that I'm showing you here were all PyCVC workflows. They were submitted from one user, and it totaled 3,795 jobs. When we were doing this work, we were sort of testing some things out, and so there's a lot of job failures in there. We have cumulative wall time, and over here we have integrity failures, and there's none, which is great. We show CPU models used, wall time per CPU model. Here you can see number of jobs finishing for a specific workflow. Then we have the duration, the job duration distribution. And then, so these 3 plots right here, filter rate per core, templates per core, fraction of time doing setup operations. These are specific to PyCVC workflow runs. And before I mentioned that when we worked on Pegasus for the Dibbs project, we developed extensions to capture runtime metadata. And so that's the kind of data that's coming from PyCVC that's being used for these plots. So that's a use case where, you know, if your application has like specific metadata and you want to plot it, we have a solution for that, and I'll go over that later on in the demo. Down here, we just show job successes to failures, average job duration, if your workflow has any integrity failures, and if they do, which workflows have those integrity failures, so you can quickly identify them. So for our own purposes, we have deployed a 3-node Elasticsearch cluster on 3 VMs. We have single instances of Logstash and RabbitMQ, and so far we haven't run into any problems with that. So not only do we collect Pegasus workflow related data with this setup, but also open science grid data, and then also some system data that we use for internal use and monitoring. In terms of research, this setup has proved pretty useful for us for several projects. So first we have the Panorama 360 project, which is about performance data capture and analysis for end-to-end scientific workflows. And here, machine learning techniques are used for workflow analysis and infrastructure type troubleshooting. Then we also have the IRIS project, where we explore methods for automatically detecting, diagnosing, and pinpointing the source of any kind of unintentional integrity anomalies in scientific workflows that are executed on distributed infrastructures. So we've made really good use of this setup for getting data for our research needs. Okay, so that pretty much covers the data collection and monitoring pipeline. Now I'm going to share with you how you guys can get started using this for your own work. So the first thing that you're going to need is a single host machine that has a static IP address. In this example, we'll assume this to be dibbs.isi.edu. And also, that host is going to need the following ports here to be unused because the services that we're going to start up will need to access them. Regarding software, you're going to need Docker and Docker Compose. And also note that for the sake of this tutorial, we'll be setting up the entire pipeline on a single host. However, for production purposes, you would likely run these services on multiple hosts. So the next step is to simply clone the repository that we have here. Everything is packaged in there. Once you've done that, you're going to be sure to give read and write permissions to the following directories as these services will read and write to and from them. After that, basically you just cd into the directory, and then you're going to run Docker Compose up or Docker Compose up-d if you want to run in detached mode. So at this point, all of the services you see here on the right will be started up on your host machine. And that's basically it. You have the whole pipeline set up with all the components connected to each other. So from data collection to visualization, data exploration, you'll be able to do that. And you just need to go to these URLs here. So now when you start running workflows, you will need to modify your Pegasus configuration file so that workflow data can be sent to the data collection pipeline. As you can see in this figure, just add the following lines to your pegasus.conf file, and that lets Pegasus Monitor D know where to send the data. So in this example, our host that we've set up the pipeline is dibbs.isi.edu. So you would set the pegasus.catalog.workflow.amqp.url accordingly as we have here. So dibbs.isi.edu, and that will establish this link right here. Note that you do need at least version 4.92 of Pegasus for this to work. And then if you want to send application-specific metadata to Elasticsearch, then in your applications, you're going to need to write the following things to standard out. So to signify the beginning of your metadata payload, you first need to write monitoring payload start, as seen here in the top left. And then immediately after that, you're going to need to write a JSON object that's formatted exactly as seen here. So we have timestamp, that's going to be a Unix timestamp. Monitoring event is going to be metadata. And then you have payload, which is a list of key value pairs specifying the metadata, the name of the metadata and the value that you want to be sent over. Then after that, you end it by writing monitor payload n to standard out, and then that will all be sent with the rest of the job information into Elasticsearch. So in the middle, this is an example of like a shell script that would be an executable in your workflow that uses this syntax to send these two metadata key value pairs. So num template blanks has a value of 3, event name has a value binary start merger. And then when you view this in Kibana, you'll see that it'll be prefixed with metadata, and then it has a name, and then the value after that. So that's how you would get started using this. And then now I'm going to be doing a demo, just basically running through the steps and going over Kibana and Grafana. So here, Okay, so here I'm on workflow.isi.edu. As in the example, you can just think of this as the dibbs.isi.edu. Up here, Dibbs data collection setup, I've already cloned the repository. So we're gonna cd into it, and here, just gonna run docker compose up. So now RabbitMQ is gonna get started, Elasticsearch, Logstash, Kibana, and Grafana. Takes maybe less than a minute to get started up. And in this demo, I will be running 2 workflows. So I have one regular workflow that I'm going to run that sends metadata using the syntax that I just went over. And then also I have a single job workflow that I'm going to submit that fails. So we can see that show up in Kibana. So to see if Elasticsearch is up and running, you can just, because it's a RESTful service, you can just curl it. So workflow.isi.edu at 200. Okay, so the Elasticsearch node is up and running. I'm going to go ahead and submit the workflows now. So okay. So now Kibana is going to be running on port 5601. So I'll go to my host. Okay, and I'm going to click on Discover. And so this is the first time I'm opening up Kibana, and data has already started flowing into our Elasticsearch instance. So we need to create an index pattern. This is pretty straightforward. So you just click create index pattern. Over here, want to select Pegasus composite events -star. And then time filter field name, we'll select timestamp. And then you're going to want to do that for workflow events as well. So now if I click on Discover, here we can see that data is flowing into our Elasticsearch instance. And we can filter down specific things. So for example, let's see, this is the successful workflow. So I can filter by username, Tanaka, which is me, submit host, submit directory. I want to look at specifically at this workflow. So I want to filter by root workflow ID. You can click on the plus sign right there. So now in the last 15 minutes, I get all of the events from that specific workflow. And then let's say I want to look at compute jobs. So I can filter for that. I just need to edit this filter, and instead of cleanup, I'll type in compute. And so here we get the metadata that we had sent over with the job. So in this executable, I just have something that sends over the bytes written for the output file. And I'm going to close this filter now. And let's see if I have the other job. Okay, so this right here is the job that failed. It ran the executable called bad executable. what's important to note here is that we could filter by status. If we wanted to find all the jobs that failed, you could filter for a non-zero status. And then if we look at standard error here, we can see that Pegasus Lite got this exit code from the job. So in that executable, I just put exit 123, and this is what we're seeing here. So it's easy to sort of debug your workflows like that. Next, if we go to Grafana, we can see the dashboard. So go to workflow.isind.edu. This is running on port 3000. Click on main. And here, set the time range to the last 30 minutes. So this is the same dashboard that I had shown previously. We have users, jobs, workflows, integrity failures, job failures, cumulative wall time, and all of this here. Of course, filter rate per core, templates per core, fraction of time doing setup operations. These were specific to PyCBC, the PyCBC application, and so these are empty. But this is just to show you that, once you start running workflows and data starts flowing in, you can immediately open up the dashboard and see what's going on. So of course we have that one failure right here. Good to know. And we have no integrity failures at all. So that basically concludes the demo. I hope this was pretty useful for you guys. Basically, you just need to clone the repo, run Docker Compose up, and you have everything set up for you. If you guys have any questions, you can feel free to reach out to me at tanaka.isi.edu. Yeah, that's it. Thank you, guys.
Yeah, thanks a lot, Ryan, for doing a great presentation. We have time and we can take some questions on right now if attendees have.
Sure.
I have one question.
Yes.
So you said that you have like 50,000 jobs, right? Or 60,000? I mean, a lot. And at least for LIGO.
Mm-hmm.
And so do you need to set up, to scale Kibana, Elasticsearch and everything? Because I think you get a lot of data at the same time. So to keep up with the throughput of the workflow, do you need to scale your setup?
So when we were running this setup during the project, the PyCBC workflows that were being run were test workflows, and so they weren't as big. They only had a couple thousand jobs. If we get to the point where we're running a lot of workflows, I mean, you may need to scale up, but the thing is, we're not getting 60 gigabytes worth of like data for each workflow run. We're just getting, the size of the documents that are being sent over to Elasticsearch. And so at some point, if enough workflows are run, yes, you could scale up mainly for storage purposes. But yeah, we haven't done that yet, but the option is there.
Okay, thanks.
Yeah.
Yeah, and on chat, we have a similar question from Patrick about sort of what hardware resources are required to set up this server. So Ryan, do you want to briefly touch that and think about the deployment we have at ISI?
Yeah, how do I see in chat here?
Below, next to your share screen option, there's a chat window, but
okay. So I guess this really depends on what kind of workload that you have and how you set things up. So for example, with RabbitMQ, we're only running one exchange and one queue, and it's already relatively lightweight. In our own setup, and this was just for, I guess, for preference, we have, 3 Elasticsearch clusters on 3 VMs, a single RabbitMQ instance on some other server in a Docker container, and a single Logstash instance in another Docker container. I'm not sure exactly what kind of hardware it's running on. That would be something that we do have to explore, for sure.
Yeah. I mean, I can tell you what we have. The RabbitMQ is a 4-core VM, 8 gigs of RAM, so nothing special. The Elasticsearch nodes are also VMs. They have 32 gigs of RAM, but I think that's, you know, we just pulled a number basically. It's not really, we haven't hit the limits here anywhere. If anywhere where you want to kind of make sure it has enough power is the RabbitMQ, right? Because if like everything downstream from that, you know, you can actually queue stuff up in RabbitMQ until you have that and kind of even it out the load downstream. But RabbitMQ would see peaks when, for example, if you start up a lot of jobs at the same time, while there's extra traffic coming into RabbitMQ. Out of RabbitMQ, it's a little bit easier to control.
Also, Mats, if I remember correctly, we've had issues with the Elasticsearch storage sizes, right? Like,
yeah, well, I mean,
the storage
they're VMs, right? I mean, it's just attach more storage. It hasn't really been a big issue. I think the other thing that we should kind of explore a little bit more is maybe, you know, what partitioning of the indexes we're doing in Elasticsearch. Right now, I think it's just a monthly index, maybe weekly. I can't remember even. But that's something that maybe, you know, if you brought in an Elasticsearch expert, they would do something different than what we have. I'm fairly sure about that, actually.
Yeah, I agree. So sometimes when you're using Grafana, and if you set the time range to be very large, I've noticed that load times can get substantial. And I don't know if that's because the way our Elasticsearch is configured. So maybe if we had things partitioned differently and they, you know, across more nodes, if that would, you know, give us any performance improvement in terms of the dashboard. But, you know, again, that's something like we do have to explore. So this is sort of like a starting point that we have right now.
All right. Any more questions? Well, I guess then, you know, we can end this office hours session. Many thanks to Ryan for doing such a great job on this presentation. And for all attendees, we are always available via email on our user support list, or you can email directly at pegasus@isi.edu if you want to know more or have further questions. And with that, we'll end this office hours session. Thank you very much.